Hello. So we're going to continue talking about the movement and manipulation of objects in games in response to external forces. But now instead of thinking about physical forces, we're going to think about functional forces or effectively, mechanisms by which objects react to one another, game state, user state, what have you. Uh, you can classify these as under autonomous agents. So if you think about a video game where you have an AI, it's not really AI in the classic definition. Algorithms that these agents use are not necessarily just AI. They can be, other things. But generally speaking, this all kind of fits under the umbrella of autonomous agents or objects that react to external state based on an internal type of logic. So, right, this is actually Unit 5. We're going to be talking about this for a little while. In Unit 4, we talked about forces of nature that are acting on objects. Next, we're going to study autonomous agents as referenced in Craig Reynolds' paper, and we're going to sort of implement these creatures that are in charge of setting their own goal and moving to realize them. And I think in this you start to realize, or you kind of start to see where a lot of the fun stuff can happen in games, where you have these external forces that apply to all objects in a game, but then also you've got these sort of internal forces in objects that then dictate their behavior. Imagine playing a game where all the other objects were controlled by other people in a different place and everybody can see exactly the same thing, right? And how interesting that is, even with a very simple set of rules. You can get to extremely deep gameplay and extremely deep experiences in that way. So now we don't always have other people that can plug in and do that. Obviously, in multiplayer games, that's kind of the way the game is designed. But we can automate a lot of those things. We can create logic and rationality and sort of these rules to sort of imitate that. And that's what we're going to talk about in this unit. So what are these autonomous agents? So effectively it's a entity, which we're familiar with already, that make their own choices about how to act with regards to an environment and, without really an influence from a leader or global plan. So it's sort of like, this is like a car driving in a parking lot freely versus a train on a pair of tracks. Ultimately, there are rules that govern the behavior of this object, right? It can't pop out of the screen clearly, and it can't do certain things. Physics will prevent it from going through walls and what have you. But outside of that, it's able to then manipulate those same laws of its environment to accomplish different things, and those objectives designate how it behaves in the experience. So agents have sort of a limited view of their environment. It's kind of like you, right? We can't see through walls. We can't see, the other side of the planet. Think about what you are aware of and what you're not. Your sense of perception is limited to what you can see, smell, taste. Even memory can be considered a perception, your perception of your past, the perception of the future, and so on. And so let's not get too philosophical there, but ultimately, when you're walking, you can see certain things, but you're not aware of like what your friend's mind is doing. You're not aware of your bank account in this moment. You have to go and look it up and stuff. So there's perception is limited, and in fact, very limited compared to what you could, in theory, expose an agent to in a video game. Where, in theory, in the video game, you have the full thing. You know exactly, the exact game state of everything. So you almost have to artificially limit the perception that your agent has. Otherwise, it's just not fun for the user, right? In theory, say we make a game of Pong, right? And the ball is here. So if we made the other player's Pong paddle exactly equal to the Y position of the ball, then it's an unbeatable game of Pong, and eventually your user is going to be really angry at you. So how do you create a Pong game where your other Pong paddle is doing things that are more interesting than just setting its value to y, where you'll never be able to win ever, right? So how do you create that intelligence? So ultimately, it's really about information processing. Your agent's going to be learning from its environment, given the inputs that it's allowed to have, and then it's going to inform a set of actions that it should take. So for example, if you see a shark, if there's a predator coming to an object that can be consumed by a predator, and its goal is to not get consumed, then it's going to try to evade that predator. Leaders are also kind of interesting, where this is actually really commonly seen in like flocks of birds, where ultimately the rules that those flocks use are quite simple. Actually, really all I'm trying to do is maintain a certain amount of distance between me and my neighbors. So you can kind of think about a radial, sort of like I'm at the center, there's a radius. I'm trying to ensure within a radius there's no other members of my group, right? And then above that, I also have, we have kind of a leader. So the general direction that we're aiming, we're all pointing or going in the same direction based on a leader that's leading us. So those are just two rules. Point at the leader, make sure that I'm not going faster to include somebody in front of me, or nobody behind me is getting into my space, and every other agent is behaving that way, right? And then you can have these leader type behaviors, where you have these flocks. And you can think about like schools of sardines, flocks of birds. It's pretty cool, and only with a very few number of rules, very simple rules. In fact, what's really nice about this, and this is called actually the behavior that emerges out of those two rules, right? Like if you were to see these two rules on paper, like stay this far away and point in the direction of somebody, you wouldn't necessarily jump to the conclusion that it's going to create this particular pattern or behavior. But that is what's called a emergent behavior that emerges out of these simple rules. It's pretty cool stuff. So we're going to use a behavior used by Reynolds called steering. Steering just applies a force to alter your velocity to best realize a goal. The force is going to be your desired velocity minus your current velocity. And then effectively you need to be in the local coordinate system of the world to do so. So let's take a look at one of these steering algorithms. We will allow programmed elements to sort of navigate in a lifelike manner, to flee, to seek things out, to pursue something, to evade something, and to arrive at a location. And using these kind of above 5 behaviors, we'll then also be able to apply path following, leader following, and even queuing, which we'll talk about. So take a minute. This was obviously supposed to be an in-class lecture, where you would do this in a group. So if you have a friend and you're watching this lecture together, which is very flattering, take a minute, talk amongst yourselves, pause the video, and think about, what do you think these behaviors are? What's seeking? What is fleeing? What is pursuing? What is evading? What is arrival? And how are they similar or different from the other behaviors? How is seeking different than fleeing, and so on? So pause the video, have a think, and then we'll talk about it. So to seek is exactly what it sounds like, right? You're effectively going to move in the direction of your target. So actually a pretty simple thing. It's not too complicated, right? So in fact, we could probably do a little bit of a demo. So in the background here, I've got my previous game that we're working on, and let me add and create a 2D object. Well, let me do a 3D object, like a sphere. Great. Which we cannot see for some reason. Let's put it at 0. Right? And what we're going to do is we're going to create a new script called seek behave. Okay, cool. Where did it go? There it is. So then we're going to create, hold on while I pause to look up the semantics. Okay, so we'll create a public game object target, and in here we're going to set the target game object to be the vehicle sprite. Okay, cool. So now when I play my game, so let's try to implement seeking in this. So in here, what I want to do is I want to aim, so my vector 3v direction is going to be equal to my transform dot position target dot transform dot position, and then normalize that. Let's also add a public float speed, and let's initialize it to 10%. And then now all we're going to do per this is we're going to point in a particular direction. I used a sphere on purpose so that we don't have to set an orientation. And in fact, let me make this a little bit smaller because it's a bit large. Great. And now what we're going to do is we're going to target our position is going to be plus equal to v direction times speed. And let's see what happens with just this basic set of rules. You'll notice that the ball is actually quite quick. It's actually following me quite well. In fact, 10% seems a little bit fast even. So what we're going to do is let's make it 2% of my speed. And now you can see it's going to do this. Great. Let's make this into a prefab, just for kicks. Let's rename this to sphere behave. And let's add a bunch of these. Actually, let me put them in here so I can. And you'll notice that they'll all, well, they should all there. They should all follow my sprite. Actually, no, they're following the wrong thing. They're following a sprite that's not there. Here, what we'll do is we'll do this. There. Now they should follow my actual sprite. Cool. Now you'll notice that they'll eventually all collapse down and overlap with each other, which is no good. We'll talk about that in a minute. So now fleeing is a different behavior and actually quite simple to implement, right? Instead of adding, so let's do enum behavior. Let's do seek, flee, let's see if, I'm not actually sure if this will work. No, it does not want to do it. My lack of experience recently with C# is showing. One moment. Okay, great. So just a little bit of syntax fixing. But now we've got this, and publicly now in the inspector I can go and change the behavior to flee. And what's nice about this is now what I can do is I can switch on my object behavior and case it out onto behave. In fact, I don't like it all. Great. There we go. And now I can do object behavior.seek. Great. And now let's do the same thing for flee. And if we have flee, then we just want to go subtract. That's really it. We want to go the opposite way of everything. Right? We want to avoid. We want to get away. Here we go. So notice I'm trying to get away from me. Now another thing you might want to do with flee is you want to probably get the magnitude, the distance. So let's save that. Distance equals to v direction dot magnitude, just to save it. And we're going to not multiply this by speed so much. Well, we'll multiply by speed, but we'll also divide 1 divided by distance. So the farther away, the slower we'll move. The closer, the faster. Right? So when I get clearly close, let me just do it without this. Oh, maybe it was because I was losing the... There. Always think about casting, guys. Cool. So now, when I get close, okay, or not. Oh. No, it should be right. So I got rid of speed. Notice that they're all fleeing from me. We can do the following. If distance is less than 1. So I'm just trying to make this a little bit more interesting looking, because right now they're just going to flee all the time, and that's kind of lame. So right now they're only going to flee when I get close. Or not. One second. Okay, so I've done a couple of things that should be fun to play with. So first of all, I added a kind of system to ensure that our object doesn't fly off. And so another thing, I added velocity. So instead of the position being changed directly, we create a velocity in the direction of the object for seeking and away from the object for fleeing. For seeking, the velocity is scaled up by the distance, so the farther we are, the faster we move. And for fleeing, the closer we are, the faster we get away, so to speak. And then we constrain the position, add the position velocity times the delta time, as you remember from the previous lectures, and we set the position. And this creates a much more interesting behavior. So for example, now you can see the object, I can kind of evade it because it comes at me, but it speeds up when it's farther away from me, and it also bounces off the walls. And so just trying to, stay away from it is actually a pretty fun challenge here, right? Like it's gonna come at me based on where I am. The speed's quite fast, so maybe we should make it a bit slower, which is fun. And now if we take that same object, and I got rid of the other ones for now, and I make it flee, then allegedly it'll try to keep away from me based on where I am, which is fine. Now it's still quite fast, so let's multiply the speed there, and hopefully we'll see that it's probably going to not move very fast until I get a lot closer to it, and then it's going to try to keep away from me. Now the issue with, so now we have a bunch of these. Let's move them around a bit. In fact, how about we do the following, and this is going to be a fun thing to do. We can, instead of point position equals transform position, we can use this same little technique here, and we can randomize the height and we can randomize the value. Great. Value times world screen width height 0. Actually, we need to multiply this. We need to subtract 0.5 times 2 times 2, which what we're doing is we're just shifting it, because as you remember, we're kind of like, it's this wide, but we have negative and positive values, so what we want to do is kind of move it to the correct location, and hopefully now when we add an object, it'll randomize its position, except it's on the edges for some reason, so we what's going on? Get rid of the 2 for the time being. this to as well, because we kind of want it to be close by. We don't want it to be too spread out. So this is good. So now you can see we can kind of disperse this grouping, and I can kind of like force this one, but they'll eventually all kind of go away from and kind of collect and pool in the corner. Great. So now we can see already some cool stuff. Now pursuing is slightly different. Let's get rid of all these and go back to our code. And what we'll do is point position is equal to transform position. And let's add pursue. And so if our object behavior is pursue, it's actually quite similar to the seek and flee, but we're actually going to change this a little bit, where v direction is not going to be the transform position minus the transform minus our position. We need to get its velocity somehow. And so the way we're going to do that is without having previous knowledge, like without having access to the other object, we have to create a static, oops. Well, okay, fine, we can't do a static in C# apparently, but let's do this, private vector3 point last target position. And what we're going to do here is we're going to set our last target position to our target.transform that position. Great. And what we're going to do now is we're going to create a vector3 point predicted position, or our v predicted velocity is going to be our target's current position minus the target vector position minus the point last target position. This is from our previous frame. And this is sort of an approximate velocity of our object. And now what we can do is we're going to take our vector3 point predicted position is actually going to be our target transform position plus v predicted velocity. Keep in mind this is already in the time scale because we were measuring it in one step, so we don't have to apply the time scale again. And now we can simply use our predicted position, which now compensates where we think our object is going to be, not just where it is right now. And you'll see that the object will kind of come at you and pursue you much more accurately. And in this case, we actually want this equation, the same one as seek, and the direction is going to be normalized yet still. But the direction is going to be adjusted just slightly. So now, let's go to pursue. Okay, lovely. Okay, let's try this again. Seems to be fleeing. Why are we fleeing when we should be the one pursuing? Let's try to seek. Make sure that we didn't break something. Okay, that looks correct. Let's pursue. Still incorrect. Where's my bug? Our target transform position minus our last target position, that should be correct. Target transform position plus predicted velocity. Predicted position minus our position plus equals speed times the distance. Are we even hitting this code? Let's see. Okay, now we seem to be working. Okay. So yeah, sometimes Unity is not the best at picking up changes. You'll notice that pursue looks a lot like, seek. If we instead kind of try to, it'll always kind of go after us, and if we're not moving, you'll notice that it will eventually hit us. You can see now it's compensating for the lack of velocity as it gets closer. We can actually fix that a little bit by doing math minimum distance 1. Or we can do so this will help it, because otherwise it's gonna not ever be super fast when it gets close by. Sorry, maximum, not minimum. So now when it gets kind of closer, it'll always go a bit too fast. You can kind of see a lot of the sort of particulars of how do you implement these things, and how do you really make it interesting and fun. And it's a lot of like tweaking with these variables, right, to ensure that you get to an experience that the user can actually enjoy. Right? Sometimes the speed based on distance is actually not fun at all. So sometimes you do want to have the minimum. Okay. You can play with this all day, which we will not do. Great. Evade is very similar to pursue in that we're just doing the same thing we're doing with pursue, except we're compensating for the future location. So let's flip this around and let's change this to evade. Right? And now our predicted position is going to be minus that, and then we just subtract. We actually use this exact same code, but just in a different sort of ordering. And so what we're doing is we're figuring out where we predict our object to be, and then based on that direction, from there we go away. Like we travel the opposite direction. And so you can kind of see now, if I were to switch this to evade, we'll see very similar behavior to before, where it actually will compensate a little bit for where I'm going to be. but it's pretty hard to tell. It seems very similar. Arrival, we were kind of already doing this a little bit already, where as you seek something, you want to kind of slow down as you get closer. And you can do that by dividing by the distance, like we were doing here. So as you get closer, you can multiply by the distance, so as you get closer, your speed slows down and slows down. And so, for example, let's create seek. Seek will no longer operate on the velocity. Let's do the following. So instead of velocity, we are going to go in the direction times speed. Well, it's the same thing really, but we're just not going to. We're not going to increase. We're not going to make a plus. We're just going to set it to be equal. Right, and now eventually our object will, well, we should make it faster than that. It's quite slow now, so let's do it at 0.5. And you'll notice that it'll kind of slow down as it gets closer, and eventually it'll arrive. And the reason for that is because we're multiplying it by the distance, and as the distance is getting smaller and smaller, you get slower. You want to slow down and slow down. So kind of think about different environments. Now this is something for you to do on your own, and think about the different kinds of scenarios in which you would seek, evade, pursue, arrive, and flee. So just take a moment, pause the video, and think to yourself. So let's create these object behaviors and autonomous agents. I've already kind of been doing that in the background. And so as you were seeing before, you can do this with position, velocity, and acceleration, and then you apply those forces to kind of behave in the way that you'd expect. So let's say you're seeking an object, you're fleeing, or you're arriving in a position. Here, check out this article. This is the classic Craig Reynolds article about these behaviors, and it goes into much better depth on these subjects. But ultimately, you want to think. I didn't do this in the examples that I've been coding in the background here, but you do want to do the full shebang. You want to have mass, you want to have acceleration, velocity. You saw how the difference between setting position versus velocity versus using acceleration creates really interesting behaviors and such. So the steering force, as we were kind of seeing, right, is really just the desired velocity and minus the current velocity, which is what we've been doing. And that way, when you have a position, you want to get to a target position, your target desired velocity is, in the direction of that position. Imagine the calculation here is, I want to be here and I'm here. So if in one time step, how would I get to where I want to be? I'm going to take where I want to be minus where I am. That's the change between where I am to where I want to be. Now, physics gets in the way. We can't just, transport ourselves to where we want to be immediately. And so you have to sort of use that as a direction and create a force in that direction, if that makes any sense. So this is sort of what you start to see. And if you take a look, right, in this behavior, you'll notice that you do get these sort of nonlinear kind of movements, especially when you're dealing with objects that are moving already. So say I'm letting it move at me, you'll see that it'll keep, well, right now we're not doing this correctly, right? We changed this, the velocity is not being accelerated. So now that we're accelerating the velocity in the direction that we want to go, you'll notice that if I sort of stay in the same place, whoa, that's way too fast. Right, if I sort of try to stay in the same place, it'll have to, the object will have to turn to compensate for my position. Okay, so additional things that you probably want to store is you want to store your forward vector, like where are you pointing. In this way, we can keep it up to date. We can use it for predicting the direction that you want to apply your force, like your thrust. Your right vector, this is a perpendicular vector to where you are. This is something that we could use, for example, if you wanted to create a system that allows you to go to strafe left and right, to kind of nudge left and right, or other behaviors as well. In 2D, you should be able to intuit how to get the perpendicular vector to your forward vector. It's just the reciprocal, right? In 3D, the math gets a little bit different, but still not too difficult to kind of figure out once you have a sort of frame of reference. You also probably want to maintain maximum speed and a maximum force, otherwise things can get out of hand. Like for example, in this demo, you can see if I set the speed to 5 and I let it go, it can behave quite irrationally with all of the different pieces. And so if to do that, all I have to do, right, is where I apply my velocity, right, v velocity, can I clamp? Magnitude is greater than max speed, right? Let's call this public float max speed is equal to 1, say, right? If my magnitude is greater than max speed, right, then I want my velocity to be scaled down by that. Sorry. When I do this again, 1 second, pause. Okay, sorry. So if I want to make sure that my velocity doesn't exceed a particular speed, I can just multiply it when I measure the magnitude and ensure that it doesn't exceed that particular speed. So now, hopefully, even though it's super fast, we'll never quite accelerate faster than 1. Right? You can see that the change in the direction is quite quick compared to before, because in the change of direction, the velocity magnitude is not quite that large, and it responds to my movement location quite quickly. Whereas if I set this, for example, to the maximum speed I can set to, say, 2, it still creates a much more reasonable experience for the user. Say this is a projectile that I want to evade. Right, I need to change it here. As you can see, it's a little bit more of a fun type of experience. Whoops, okay, cool. So obviously the radius and the mass, these are bounding things that you want to use for collisions and detection of those collisions. Right, so can I use back and left instead? Forward and right are the standard way to talk about these things. That is true. Forward sometimes is considered look or direction. Back and left. The issue with that is, so the issue with left is that you're generally use the right-handed coordinate system, and so I don't know, I don't know about industry standards because OpenGL and DirectX have different standards in terms of like frame of reference. Ultimately, stick to your set of conventions or whatever convention set is being used by you or your team or your company or your group. And we'll talk about these more next time. So what we can do with the forward and right vectors, we can use the forward vector to figure out where we're pointing and which direction to apply a force. And the right vector is can be used to determine whether or not objects are to your left or to your right, and also apply forces in the direction of the right vector. As you know, the velocity is applied in the direction of forward, and so it's the same vector. You just have to ultimately normalize it. And to calculate the right vectors we talked about before, it's ultimately the reciprocal in 2D, which you take the x and y and flip it, and then you flip the sign of the y value. Wait, no. That's not always true, is it? No, you negate. Right, if you're trying to get if you have a vector and you want to get your left vector, you flip them, and then you negate the x value. If you want to take the right, you flip them, and then you negate the y value. If you want to get your back, you just multiply it by -1. Sorry, got turned around there for a second. So we've already talked a little bit about this algorithm. This is sort of the algorithm that we would implement. We kind of went through this a little bit in the code earlier, right? We want our velocity, our desired velocity is our position, or the target position minus our position. We set the magnitude to the speed, and then we apply a force in the desired, which is the velocity, our desired velocity minus velocity. This is not something that I implemented in the demo. I actually did it at the with accelerations. But to convert accelerations into forces, you divide it by the mass. And so if the seek method returns a vector, then what we have then, the path, which describes that vector, we'll get a kind of a path out of that will guide the movement of the object. And so this is to apply that seek vector, as we mentioned, it's by way of a force or a velocity, or we just add it to the acceleration like we were doing in the demo earlier. So if we have a function like apply force, like we did in the previous example in the forces unit, we would do it there. And I didn't do that in the demo in this lecture, but it should be kind of a project for you guys to go and do that yourself in the exercises and assignments. So finally, some homework to read. Read the chapter on autonomous agents. You probably already read this, but please do. The classic Reynolds paper this is the link. And also, please read the steering behaviors introduction, seek, flee, pursuit, evasion, specifically in the Kragers-Reynolds paper. You don't have to read the whole thing, but I'm sure you could benefit from reading all of it. And that's it. So it's pretty fun. I'll do a little last thing here. I'm gonna pause the video and add some fun. Add some fun examples. Okay. So what I did is I did a kind of interesting thing where I created a new kind of behavior built on the existing ones. So all of the balls will seek each other, but if they get too close, they flee. And that's kind of that emergent behavior I was talking about. So now what will happen is now you'll see they'll all sort of clump together, but they'll never quite intersect, and they'll even bounce off of these walls in this kind of almost arbitrary pattern. Now, it's not quite arbitrary, but it is kind of funky looking. It's not pre-programmed, it's just sort of behavior as a result of the constraints of the system. As they get too close to a wall, Some of them will bounce, creating kind of compression, and the other ones will go in different directions. It's pretty fun to watch. In fact, you can sort of multiply this out. And I've repeated I'll show you the code in a minute, but I repeated that sort of like random initialization. As you do this, you'll create more larger and larger sort of clumps. If you want the clumps to be more spread out, you can actually change that distance, right, at which they'll start to flee. So the idea here is that they're seeking each other. They're all seeking each other. Every single one of them. It's like a for loop, and they're all going in each one. So this is not exactly a performant piece of code. And when they get too close, instead of seeking, they flee. And then once they do, they're kind of stuck in this sort of loop. In fact, if I do and I add the ship, so this is working under a tag system, so anything tagged thingy they'll try to avoid or seek. And so what will happen if I add thingy to the ship, right, they'll actually try to seek the ship as well, but also avoid it. So they'll kind of do this funny behavior here. And then if I try to fly through in the middle of it, I might be able to kind of split it in half. You can see that it'll... in fact, if I want to create a new tag, so for the vehicle, I'm going to create a new tag called avoid, right? And now that the vehicle is going to be avoid. And if I go here, and I'll do this, bool f avoid equals false, else if object tag equals avoid. In that case, f avoid equals true. And then we'll do else if object thingy not equal. Cool. And if f avoid is true, so if f avoid is true, or the distance is too close, then avoid. And now what will happen is anything with the tag avoid will be avoided. And that what I'm trying to do here, and let me create a lot of these, and let me also increase the distance just a little bit more, so we have more of a cloud to play with. Again, this is not particularly performant. You can see it'll create a little thing in the center there. It's trying to avoid me. Oop, where am I gonna go? There it goes. And notice that now it's trying to avoid the ship. And another thing I can do to kind of play with this is I can use this tag that if I'm avoiding, instead of doing this calculation, if I'm avoiding, I'm going to multiply my speed by 5, and I'm going to get rid of this distance. And we'll see. What I'm trying to do is I'm trying to get them to disperse, to break the bonds. Right, so here, oops, if I get too close, actually I do need this times 1 over distance, but I want to have the math f max or minimum of, call it 0.5 or 0. Yeah, I'll just keep the I'll just keep this distance, but I'll multiply this by 25. So it's going to be really aggressive, but when it's far away, it won't really be affected that much. So you'll see, feel a general dispersion. Another thing we can do is we can do math to the power, this to the power of, say, 10. So when we're really far away, we won't feel it, but when we get close, it'll just explode. That's kind of what we want. You can kind of see, even if I go 100, it'll almost create like a barrier. I'm not sure why those are stuck now. Maybe some weird truncation errors causing that, not a number issues, and then it gets stuck. You'll hit those once in a while, but now you can see, cool, it's fun. Create a barrier around the ship because of this behavior. It's fun. Yeah. So there you go. That's kind of it. There's not too much more to talk about there. And so yeah, you can do some really fun things with these behaviors, applying forces, aggregating velocities and accelerations. And so yeah, this should be really fun to do, and I really recommend reading up on the different behaviors that you can implement to and explore further. Awesome. See you guys next time.